6:01. All right. Thought we were late. Okay. We have a lot of stuff to cover tonight, and we know that often these things run long. So we're going to move really, really quickly. What I've done is put up some of the first instructions that I need you guys to follow right here. Basically, you're going to download a repo from GitHub, and if you follow the README in that GitHub, it will have you start installing your environment, installing Rust, installing any auxiliary tools. So while you are doing that, uh, I can go through the regular preamble that I talk about in the group, and that way we can multitask and save some time. So welcome everyone. Thank you for coming to the November Rust meetup. I just wanted to remind everyone that we are operate under two codes of conduct, the Rust Code of Conduct, as well as Microsoft, who are the generous hosts here for us today. The codes of conduct are very straightforward. They're very short, but they basically say, please treat each other with dignity and respect. So if you feel that somebody is not treating you with dignity and respect, please let them know. They may not realize that they are doing something offensive. If the behavior persists, then please let me know, and I'll step in to help fix the situation. Okay, so beyond that, we are here this month on the second Thursday. Next month, we will also, because of the holidays that come later in the month, next month, because of Christmas holidays, we will also be here on the second Thursday. And so that is December 14th. I will quickly, December 12th, which will be the second Thursday of next month as well. We usually meet on the third Thursday, not the second, so I want to make sure you guys are aware of that. All right, so beyond that, you guys, for those of you, anybody new here? Wow, we've got good half the room is new. Okay, so my name is Brad Gibson. Do a quick give the introduction for those who don't know me. I'm U007D online. You'll be able to find me on most, any technical forum under that handle. I actually began tech a long time ago with dinosaurs running around my backyard. And I didn't know it at the time, but I really enjoyed a lot of low-level work and what we would now call systems programming. But at that time, there wasn't a lot of anything else. So we just called it programming. So I'm trying to run a series of hands-on workshops to help folks discover the joy of low-level programming. I think systems today are huge and complicated, and they're very, very difficult to access the way we did back in the day. So if we can help people discover a way in, particularly with Rust and some of the great tooling that we have, I think we can create a whole new generation of people that falls in love with tinkering with hardware. So that's the hope, that's the aim, and we'll chip away at it a little bit at a time. Come on in, everyone. Okay, so the next thing we've got to take care of is most of you probably do not have the hardware debug probe. So for anybody looking for the hardware debug probe, I bought 36 of these, and so we've got one for everyone here if you want one. They're $13.60 is what it will come to. U007D is my, whatever they call it, name on Venmo. If you want to pay me there. If you don't want to, if you don't have a Venmo account, I will take cash, and but I don't have any change or anything like that. So we'll do that. And I never want cost to be a blocker to anyone. So if the cost is a factor, just let me know, and I'd be happy to donate this to you. So no matter what, everybody gets to play. So let's hand these out. Who needs one for debugger tonight? Okay, debugger. So are you just going to pay me on Venmo? Yeah. Okay. All right. Otherwise, just need 1360. You'll need, oh, you've got one already, so you don't need another one, right? Anyone else? One, nothing? Okay, you do need one? Okay. Okay. Two more. Can you raise your hands if you need one so I can count out how many? 1, 2, 3, 4. Says 4 more. Okay, great. There you go. There you go. 1360. Yep. Yes. Oh, you have to click the Wi-Fi icon on your computer. Then you'll get a little Microsoft this thing. And then you have to join the MS event, not as guest. You have to use the blue one. And then the password is reactor11/13, all lowercase, no spaces.
Yes. Connect.
I only got one. Try connect. Okay, try guest.
This one here.
You should get a little dialogue that asks you to, if you're a green button for a guest and a blue button for an event, and you click event. Okay. Okay. Somebody else ask for one? I have a bunch. So 1360. Anyone else need one? Hardware debugger? That looks like me. Yeah, Brad Gibson. Hardware debugger? Okay. Okay. All right, so for anyone who is new to the group, we also operate our own Discord server. So our Discord server is a great way to connect with folks between meetings, get help. Maybe if you're tinkering on something, I guarantee you there's somebody else in this group who's tinkered with it, who's probably run into the same kinds of bugs that you're experiencing right now, and you do very well to just, hey everybody, anybody seen this before? And somebody can sort of help you get through it. So it's great to have a little bit of a community like that. Okay. After we meet, does anyone need the URL for the repo anymore? Oops, where did that go? There it is. Anyone? We're all good? Okay. So after the meeting, we often get together at Flat Stick Pub, which is a pub down at Redmond Town Center. And this is a way to socialize and talk a little bit about what we did or didn't get done at the meeting. Or if a topic of discussion comes up and you're interested in it, we can follow up with it there. We will get the recordings for these meetings, and I'll be posting them up on YouTube. So for folks who don't get a chance to make it, you'll be able to see them on YouTube. We did not get a recording for last month's meeting from Microsoft, so I don't have anything posted yet. I'll check on it though and see if we can get it. As always, call for speakers. If you're working on something or you have a topic that you think might be of interest to the rest of the group, please reach out to me. We've booked, obviously tonight, we've booked December and we're booking into January now for speakers. You can talk about something at an intermediate, at an advanced, or at a beginner level. Fully half of the people in our group identify themselves as beginners. So beginner topics are most welcome. A couple of announcements in the ecosystem, especially applicable to tonight. For dealing with errors, this error is probably the most popular crate for dealing with a certain type of bespoke errors in the Rust ecosystem. Very recently, the version 2 got released, which is no-stud compatible. So you can now use all of the facilities that this error has available in your embedded systems development. Further, because this is we live in a golden age here. There's another crate called Derive More that has moved into the same territory. And it turns out that Derive More does an even better job at getting rid of boilerplate and managing bespoke errors than this error does. Neither of them, for the intermediate advanced folks, neither of them appear in your applications API. So you can use it for libraries and not have to worry about breaking changes and so on. In the code that we'll be running tonight, I actually did use derive more. It's my first time using it, and aside from a couple of sort of getting started hiccups, it was fantastic. And I also love this error, so it's great to have a choice. All right, so let's talk about bare metal debugging on a Raspberry Pi Pico and Rust. So for those on streaming, I'm going to try to. I have a very small board here that you won't be able to see very well, but there's a green board on here. I have a little tripod, and I was going to mount my camera, but my camera is not or my phone is not able to join the Teams presentation, so I can't show the video out of this camera. I'll have to work on that for a future talk. But this board, this green board, is our Raspberry Pi Pico. It's about $4. This is a Pico W, so I guess it's $6. These are not expensive boards. They have an incredible amount of horsepower on them. And what we're doing is we're learning how to program these boards in Rust with no operating system. That's what we mean when we say bare metal. There's no Linux, there's no Windows, there's no Mac OS. There's nothing between your code and the hardware. So another way to think of this is the code that you're writing is the operating system. Okay, so when you're thinking about threads, there are no threads. That's an operating system concept. Processes, preemption, those things, scheduling, those are all operating system concepts. Heap memory, allocation on heap memory, operating system concepts. We don't have any of that good stuff. And so we're going to be writing programs on the metal as the operating system itself, and then we can build up layers over time. Any questions about that? No? Cool. All right, let's get started. So one of the things, this is the first page on the deck that I showed you already. One of the things I'm going to try to do tonight too is also equip you to do this on your own. It would be actually a lot faster if we just went through the exercise and got the light blinking, but then when you stepped out of here, because we're on a guided path, it would seem really easy. Then when you stepped out of here, you would run into brick wall after brick wall. And as I said earlier, we want the passion, the excitement, the fun to come through. So I want to spend some time, maybe 15 minutes tonight, to help you get through some of the roadblocks that you're almost certainly going to encounter when you do this on your own. So we're going to set up our environment to compile code for the Raspberry Pi Pico. What does that mean exactly? What is a compiler doing? It's taking your text, what we call your source code, and it's translating it to binary or executable machine language. Well, what is machine language? We've heard of machine language. You might have heard of assembly language. What are they? Well, there's basically a one-to-one relationship between machine language and assembly language. Machine language is the binary ones and zeros that the processor understands. When we're reading ones and zeros, it's very hard for us to see the meaning in that. And so we make a one-to-one translation where a chunk of ones and zeros represents a word. And those words map to those bit patterns, and we can read the words as human beings much easier. It's just a one-to-one mapping. So it's fairly interchangeable to talk about assembly language, which is the human readable form of machine language. But machine languages are not all the same. If you write a program and compile it for an Intel chip and then load it on an ARM chip or a RISC-V chip or a PowerPC chip, it will not run. And so each chip type has its own language. So the technical term for that is instruction set architecture, ISA. Each chip has its own ISA. Now, it's not every chip. Intel has a whole family of chips that run the same ISA. You can buy a Core i5, you can buy a Core i9, right? ARM has a whole family of chips that run the same ISA. But sometimes you move your chips from 32-bit to 64-bit. That sounds great. That's going to be a different ISA, even within the same family. So there are many different ISAs within Intel. There are many different ISAs within ARM. And there are obviously different ISAs between the two manufacturers. So what we have to think about when we are compiling is we are trying to translate our text of our source code to the instruction set architecture of the board we're running on. That's what we need to do. So that's referred to as a target triple. And for whatever reason, the target triple is often not three things, but it does talk about what the ISA is. It talks about who made the ISA. It'll talk about what OS it's under and a couple of other parameters. And we'll see what these look like. But when you're doing embedded systems development, you need to know what the target triple is that you're going to run your code on. Otherwise, you can't compile for it. Okay, so let's start with what processor do we have? First thing you want to do is type into a search engine what board you have, because you probably know what board you have because you bought it. Raspberry Pi Pico. And you're generally looking for what's called a data sheet. The data sheets will give you lots of technical information. They come in at least two flavors, and it's almost always the abbreviated electrical data sheet that's going to come up first, and it's actually not the one you want. You want the big, thick, scary one. Now, we're only going to dive in. Like some of these are 600-800 pages long. They're seriously large. But we're only going to dive into the first 10 or 15 pages and only looking for just a few little pieces of information. And once you get into the habit of doing that, the big, scary document won't be so scary anymore. So you do your search for the data sheet. You can see something comes up here for Raspberry Pi Pico. If you click on that, you'll get taken to a PDF by the Raspberry Pi Foundation. And on page 3, it'll say that the CPU in the Raspberry Pi Pico is a dual-core ARM Cortex M0 Plus running at 133 megahertz. You're like, great, how do I use that? Well, that is not a target triple. That's a description of the microcontroller that's in the Raspberry Pi Pico. So we got to keep going. But that is a clue. So we're going to go back to our search engine. We're going to search for the Cortex M0 Plus. And we're going to look for that data sheet. And sure enough, on ARM's website, you get the processor data sheet. It's no longer the board. There can be many different boards that have this processor on it. So now when we look at the ARM Cortex M0 Plus data sheet, you can see that it's telling you what the architecture is, the instruction set architecture, that ISA that's so important. And it says it's ARM v6M. What does that mean? We won't get into that here. But that's the instruction set architecture you're running. That is not a target triple, so the compiler will not understand that. So we have one more step to go through. We go back to our search engine. We type in Rust platform support, and we get a link to all of the different instruction set architectures that Rust will support. And it maps the architecture, the ISA, to the target triple, which is the instruction you need to tell the compiler. So that's our final step. So here, scrolling through a list, what we do is we find that on the right, it'll say ARM v6M. And then on the left, if we go over, we have something that looks like three things. Thumb v6M, none IABI. These are all really weird words. We could talk at, maybe after about what thumb means and what the M means and what IABI means. But this is the name of the target triple, and that is a string that your compiler will understand, and we will need that. So this is important. If you go and get yourself a Raspberry Pi Pico 2, it is not running the same microcontroller as what our Pi Pico 1 is. You'll have to do this process over again. You'll come up with a different target triple that you can compile the same application for to try to run it on the Pico 2. The booting of each board is a little different, so you may run into some boot problems. But other than that, it's generally going to work. So on my particular system, if I ask Rust, what are the architectures or the target triples you understand, it will say, hey, I know how to compile for AArch64 Apple, which is Mac OS. I know how to compile for 64-bit bare metal ARM chips. I know how to compile for 32-bit RISC-V chips. I can do a Thumb V7, which is another kind of ARM chip, and I can do WASM. Now that just happens to be what I've installed on my machine. None of that is Thumb V6, which means if I try to compile, whatever I compile will not run. So we install the target triple, and I learned tonight that install is a undocumented command. Should probably say rust up target add, but it works the same. So if you type in rust up target install thumb v6 -none -iabi, the tool will start downloading. And you should probably do this because if you don't have your Thumb V6, you're going to need this for tonight. It's in one of the steps in the README. Then when we're done, you can see that now there is a Thumb V6M entry. So now our compiler understands how to compile for that. We just have to ask for it. By default, your Rust compiler will compile for your host target architecture, the machine it's running on. And we're going to be targeting a remote architecture. So those terms are important. Now that we've taught the compiler what to do, we have to find a way to have the host machine talk to the target machine. And this is the complex part. For any of you who've done embedded systems in the past using C or C++, you know how complicated this can be. Well, like I said earlier, we are living in a golden age. We've got some really nice tools today. Now, some of these tools are still early in their development, so we might see a little bit of flakiness today, but the experience of working with these tools is really, really smooth. A note after installing Probe RS tools, if you're running Linux, you may have to modify your UDEV rules in order to get this to work properly. That applies only to Linux users. So if you run into that, have a look at this slide deck, raise your hand. I can try to get you the link. And there's an article I can send you to that you can walk through to set up the rules for security to allow you to do the things that need to get done. All right. I guess from this point, let's move over to the code base because we're basically going to run the code. I don't want to switch that. So here we are. I'm going to use the IDE that I am most familiar with for as long as I can. And then there's going to be a, that is very strange. I would like this to not switch my screen. I would just like it to get out of the way. All right. All right, so I have cloned the Blinky Probe repo. This repo, if you've cloned it, and let me talk about how we hook up our equipment first as well. In the repo that's in the README on that repo, there's a link to a schematic, and the schematic is very simple for those who did the last one compared to what we've done before. And thanks to Carl for helping me debug some errors that I made when I was writing up my schematic. You rock, Carl, for sure. But your board should look like this. Okay? What we're doing here, and I'm sorry for the folks on stream, have a look at the README and click on the schematic diagram, and you'll see a diagram of this. What you have is a board. This board is going to be powered through its USB port. And what we're going to be doing is we're going to be writing software that runs on this little black square. That's the Cortex M0 Plus. And that software on that little black square will either put 3.3 volts of power through any one of these pins along either side, almost any one of these pins along either side, or it will detect whether or not there are 3.3 volts of power on that pin coming from somewhere else. And that's really what it's doing. Now we have a fancy name for that. It's called GPIO, General Purpose Input Output. So what we're going to do is our software is going to communicate with the real world via GPIO pins. We're going to tell the pin, you be an output pin, and I will use software control to tell you whether to output 3 volts or not. That's all we're going to get with our pins tonight. Or we're going to tell the chip to configure the pin to be an input pin, and then we'll be able to read memory to find out whether or not we have voltage on that pin or not. It'll show up as a 1 if it sees voltage or a 0 if it doesn't. And that's the essence of communicating with the real world in software. And as we'll see in the code, it gets interesting just even with that simple world. So let's start by plugging things in. Your debug probe has sort of 2 ports on the end. One port ends with 3 little pins here. These are your serial pins, transmit, receive, and ground. They will go into GPIO pins 1, 2, and 3 way up in this corner, but we're not going to need them tonight. So that's why they're not connected. We will be able to do debug print statements in our embedded code, which is actually a big deal. It's not easy to do that without plugging in these serial pins, without configuring your serial port, without 8N1 stop bits and parity and all the stuff that goes along with it. We don't have to worry about any of that. So what we will hook up is the SWD cable, right? And that's the protocol that this probe is using to talk to this board. What's it doing? Ultimately, this is another Raspberry Pi Pico, so it's kind of confusing, but you don't have to worry about that. This is simply a computer that is going to control this processor. Ultimately, it can tell it to stop, to back up, to move forward, to do whatever it wants. It's under your Pico will be under the control of this probe, and that's what's going to give us the power ultimately to debug. So we're going to take the little plug here. It is keyed, so you have to put it in exact. It only goes in one way. And it goes right in the top of this board, like so. Okay. And that's it. It only goes in one way. Question? Yeah. Is it a Raspberry Pi Pico? Your board doesn't have me. Yeah. The headers are just allowing you to. Raspberry Pi Pico. That's weird. You are right. You actually, they didn't solder it on. Do you see where it says debug?
Yeah, no, I saw those.
So
I'm trying to find the wiring diagram online. I don't know which order to put the 3 pins in.
yeah, so they didn't solder your socket in. So you might be able to use this in the SWD port.
Yeah, that's what I'm trying to do.
Yeah.
I need to know the order.
Yeah.
Pins go in.
All right. Have a look for that order. If you can't find it, I will. At break time, what we'll do is we'll take a look and see if we can find the order. But I think they are the same on this end, so you should be able to do that, as if you know the right order. Yeah.
It's on those.
Yeah. Yeah, I was going to say, looking at the.
Red side is facing gold thing. Red side is facing outwards back. That answers my question.
Okay, yeah, it looks like it's straight through wiring. Okay. All right, any other questions about the wiring? Okay, so now, next step, we're going to plug in the probe, and you should get a red light on the probe. And then next step. we will plug in the Pico, and nothing should happen. Yep, the probe needs its own power, and the probe does not supply power to the Pico. So once your probe has power, and once your board has power, cargo run the repo. You should see it compiling. You see it pushing code to your board. And if everything is wired correctly, you will have a flashing light. No. Yeah, this code, by the way, the code that we're looking at tonight was inspired by Carl. Carl had a great idea about, oh, it's completely different. Yeah, and I did that for reasons we'll get into in a minute. But yes, it's not at all the same. Okay, so what you have now is this processor is running the code, which is flashing a little LED. And if you push the button, the LED will cycle through 4 modes. This is fast flash mode. This is slow flash mode. Then there's on, and then there's off. And then you're back to fast flash again. And if you want to get really fancy, let's say we're in some random mode, and you need to get back to fast flash right away, but you don't want to go through the other ones, you can actually long press the button. And then if you do that, it'll go right back to fast flash. Whoa. Okay, that is what the code does. So the reason why I think this is great, and thank you again, Carl, for this code, is it's pretty simple, but it's just complex enough to make this whole problem interesting. And I think it's not easy to find that sweet spot. So hat tip to Carl for that. Okay. Any questions? We all good? Yes, sir. Yeah. Might be a UDEV error. Don't know exactly. Let's see. It says probe cargo run failed to open the debug probe, and your debug probe, the selected debug probe was not found. This can be due to permissions. Pretty sure that's the UDEV problem. Yeah. So let me jump over. There may be some folks on the there might be some folks on the teams that are running into this problem as well. So let's see if I can find you. A friend of mine in Germany has written a really good primer on doing this. And yeah, so I would say have a look at archive.hannobron.com. And then you want to scroll down to where they start talking about UDEV rules. And they actually put some more, there's more detail actually in the, maybe even start in the probe.rs docs, because that would be at most up to date. There we go. So probe.rs docs, and then if you scroll down to getting started and probe setup, you will be able to find the Linux UDEV rules that need to be set up in order for this to work in some cases. Okay. So yeah, so you just go to probe.rs and you can click documentation, getting started, and probe setup. Yes. Yes. Yes, you can. In fact, that's what we did up till today. Okay. You can just use your USB port. There was a different tool we used, not probe.rs. It was Anybody remember the name of it? ELF2RS, thank you, yeah. And so if you use that utility, it's designed to work. You will not get the ability to actually do debugging, but it will deliver the code and flash the code onto the board, depending on the board. Yeah. Great question. The question was, how does cargo run end up invoking probe.rs and doing all this work? How does that work? Did you get the probe.rs documentation? Mr. Lightning, I forgot your name. Apologies. Matt. Okay. Did you get the URL here? Okay. Yep. Okay. Great. All right. So this is another really nice thing about Rust, is it's highly configurable. One of the things I love to do is download a Rust repo and build it. I didn't used to say that when I was programming in C++ and C, because it was really hard, right? So now we have .cargo config.toml, and what you can do is you can explain to the Rust compiler how you want it to run when you say cargo run. So this allows you to change the semantic or change the specifics in order to preserve the semantics. And so when you're running in this repo, because this repo is designed to talk to a remote board, cargo run means compile and push that baby over the wire into my board. You don't have to worry about it every time. So it's in the root of the crate .cargo/config.toml. You can see that the runner is set to probe-rs. And so when you say cargo run, it's whatever is in that line is what's going to actually get executed. Questions about anything else so far? Yes, sir. Yes. So the question was, is this on this runner line, is this configurable for different boards? The answer is yes, it is. So probe.r, you can actually run a different tool, and we were running a different tool up until today. I guess it was ELF2RS would have been here. Completely different tool. That tool does not work with probe hardware. It's just straight through a USB cable. So you can run any command you want. Hopefully the command makes sense, otherwise you'll get an error. And in this case, this command does work with a huge number of chips. If I can ask. Okay, ELF2UF2-RS, thank you. I don't want to list the probes. I want to know all the probes. Maybe some, oh yeah, supported chip. List. All right. Okay, this is a good list. No, probe.rs is a tool written in Rust. I'll take you to their website so you can see what they're trying to do. They're trying to bring embedded systems development into a more modern age, because anyone who's done it before, it's arcane. The commands you type are hundreds of characters long just to do a cargo run. Yeah, and you put it in a script, and then sometimes the script doesn't work because of the bash and the quotes, and it's ridiculous. It's amazing anybody even wants to do it. So probe, the RS is trying to say, look, let's build a tool that makes embedded systems more like using any other appliance. We'll give you all the flexibility, but this isn't the dark ages anymore. And it's written in Rust, and it's primarily the Rust community, by the Rust community for the Rust community. But it turns out it's useful everywhere, and so that's why this tool is for anyone. So, you know, they're talking about what ISAs they support. They're talking about what probes, what hardware probes they support. We picked this one because it's inexpensive. That Seger one has multi-$100 probes. And it's because the whole system has been, the whole ecosystem has been so locked down that no one gets, there's no competition. So that's changing now. And so we can buy $13 probes and use, you know, world-class probe software with it. Yeah. Yeah, RP2040 is the name of the microcontroller on the Raspberry Pi. Yep. That's right. Right. So the question was, can through that dash chip parameter, can we do other chips, other Raspberry Pis? Yes, we can do other Raspberry Pis. We can do other non-Raspberry Pis. Every line of this list I'm scrolling through right now are the chips that you can put there instead of RP2040. Correct. The fact that the probe itself happens to be an RP2040 Raspberry Pi Pico is irrelevant. Think of it as a black box and it just does this thing. And that we are not compiling for the probe. The probe is just moving the data through. We are compiling for the remote target, which is our board. And you could use any of these boards instead. But yeah, thank you for clarifying that. We're not targeting the probe itself. Yes. In config.toml, are you able to change your target for what? Oh, yeah, change parameters for the target you're compiling for. The answer is yes. Yeah. Mm-hmm. Sure. Yeah. Yeah, there are ways to configure this. The aliasing capability is somewhat limited. So sometimes you can actually make a new command, right? Instead of saying cargo run, you can say cargo send this to, you know, my other board, right? And then that command is mapped to a different command. So there are ways to do it, but essentially, yes, you can map different commands to different boards, and if you have the same source code that is maybe conditionally compiled to work on different boards, yes, you can do that very, very easily. Yes. Okay. Wow. An unspecific error occurred. Oh, an ARM-specific error occurred. Okay, so connecting to chip is unsuccessful. That one sounds new to me. What OS are you on? Mac OS. Okay, good. Same as me.
An error occurred in the communication with the access or debug port. Target device did not respond.
Okay, so you do have the red light. You are plugged in. We are wired. Quickly debugging here.
There is one other weird thing. When I plug in the USB-C, this light turns on unless I'm holding down the white button. So hold down the white button, it doesn't turn on.
Okay, so you're on 4. Yeah, that just tells me that there's already code in here, and that code is turning on that light.
Okay, yeah, this is the same code I used for the LED.
Yeah, that's fine. That's normal. And putting it in program, this is now in program me mode, so that's why the light doesn't come on. Yeah, I can't say off the top of my head why that's not coming on. I would I'm sure you've done this already. I would double check that schematic to make sure that we are wired correctly, but it's clearly getting the right power. That's a new one for me. I'm sorry, I don't have an answer for you.
Well, thanks, I will start Googling.
Okay. All right. Any other questions, or can we keep moving? Yes, sir. Okay. Do you want to let him know just in case? Or do you want to tell him? Because I don't know that he knows. I don't have an extra one. I do have one on mine, as you can see, but I don't have an extra one with me. All right. Yeah. Oh, look, I'm rich. Thank you, sir. Yeah. Thank you. Okay. So how are we doing for time? Okay, good. All right, so now that we've got this in here, what we can see is that probe.rs is taking the compiled code. It knows where to find it in the target folder, in the debug. It knows where to find it. It is erasing the flash inside the RP2040, this RP2040. We're never mucking with that one, right? It's erasing the flash. What is the flash? The flash is like memory, but it's the reason I can turn off the power to this board, and then when I restore power, the app can, starts running again. Whatever you program into here, into this board, you're probably going to program it into the flash, just like a thumb drive, except it's built onto that black chip here. And then what you can do is when you boot up the board knows to look at the flash and it runs the code that's there. It's actually a feature called execute in place, because flash memory is not the same as what we think of when we think of RAM or memory. And so in all these cases, you have all these different devices, whether they're GPIO pins, whether they're flash memory, whether it's a bus where you're moving data back and forth. These are all devices that are inside this little black square. We call them peripherals. And those peripherals, there's maybe hundreds of them in here. There's a lot of them. These peripherals are all mapped or controllable through memory. So they're made to look like memory to the processor. So the processor just thinks it's reading and writing from memory, but in fact, in certain cases, it's actually controlling little machines, these peripherals that are on the chip. This is how we do work. This is how we control the GPIO pins and tell them to read input or to put power as output. We simply write to a space in memory that isn't actually memory. It just looks like that to the processor. Okay, so that's called memory mapping, and it is central to embedded systems programming. Any questions about memory mapping? Memory map devices, that kind of thing. Everybody gets that concept, right? Okay. So I'll try to go through this code really quickly. We'll take a break, and then we'll come back. I'll go through this code quickly. We will break the code, like break the code. Then we'll go for a break, and then we'll come back and actually start debugging to try to figure out how would we ever figure out the problem. So let's look through this code. Starting on main. Okay. What are we doing? I put a lot of comments in here because some folks here might be coming up to this code for the very first time. So I wanted folks to understand why each step was done. We are using a concept known as asynchrony. And why are we doing that? Because we want to do multiple things. This is why I said, it's hard to pick just the right level of difficulty. I want this light to flash, but I also want to know when this button is pressed. Well, I'm sure everybody here is like, I could do that without asynchrony. Like, I don't need async await to do that. I'll just turn on the light for, in this case, 250 milliseconds. And then when I'm done, I'll check the button, see if it's been pressed. And then I'll go back and turn it off for 250 milliseconds. And then I'll check the button. And you could do that. Any thoughts why we didn't do that? It's tedious. It's actually way simpler than this code, like in terms of lines of code. Yes. You'll feel that delay. 133 megahertz, it's probably a couple of microseconds. Arguably, maybe less delay than what we have. Maybe. Correct. It also needs to be pressed when you check it. Imagine we change this flashing to be on for 10 seconds and then off for 10 seconds, right? you could not change the behavior of this light until there was a transition point. Oh, I got it. I will build up 10 seconds, 100 milliseconds at a time, and then now your code stops being simple. And what if I want 150 milliseconds, right? It's a big pain. So we run into all kinds of problems doing this. And probably the main reason why we do this hasn't been mentioned yet. Carl, save power. Okay? If you're running the CPU in a hot loop, fast as it can, like go, has 100 milliseconds gone by yet? Nope, right? At 133 million times a second, you are chewing up power, and you don't need to. And then you're like, oh, is the button pressed? Is the button pressed? And it's a human. At these speeds, it's going to take forever. Yes. Right. What if you want to do virtually anything else at the same time? It's going to be impossible. So what we would like to do, sorry? Okay. That's a great comment. That's a great comment. Okay, so Carl's making the comment that he got a meter and actually measured the power, and he found out that the LED is using almost all the power, which is fairly obvious given the big old resistor that we have here that's just bleeding off the heat. But the point is that we can optimize the power usage of that CPU. This CPU is very light on power, but you could buy a Raspberry Pi 4 and a 5 and a you know, there are some like quad core 64-bit single board computers out there that are actually starting to use significant power. So if you're using a battery powered application, I can have this. Obviously, I wouldn't use a power hungry LED, but I could, by programming this asynchronously, I could actually, have battery life in the level of years by being really, really careful with power. And that's probably the main reason why we don't want a busy loop on anything. Yes, sir. Basically, the question is, does that await statement put the processor in a low power state? Not directly, but indirectly it does. The await allows the processor, if the processor will check a bunch of conditions, and if those conditions are all met, it will put itself into a low power state. And await will cause one of those conditions to be met. There may be other conditions that prevent the CPU from going into a low power state, but at least we're not the problem. And that's what we want to be able to do. Correct. That's built into the hardware of the processor, correct. So all we do is tread lightly and just don't use the CPU whenever we don't need it. And the processor will do its best to go into a low power state. It sets a timer because it knows when you want to wake up based on this event or based on that time. And then it will wake itself up and say, oh, okay, here we go. And so you save a lot of power. Oh. The async that we're using is part of the Rust programming language. Yeah, and so what it's doing is remember, there's no operating system, there's no scheduler, there's no idle thread like you might find in an OS. You are you are the process, you are the thread. So there is a piece of software that is in the library we're using called Embassy, that's just making this all easy. And that piece of software is called an executor. And that executor is running individual tasks, not unlike how you would think of threads under a normal OS. And when you say await, that is a signal to the executor that you do not want CPU time. You may want some in the future, and there's, wake me up when such and such a thing happens, when this timer expires, when this button is pressed. But you're asking the executor to take you off the CPU. And the executor is programmed very carefully to do nothing when it has no work to do. When there are no pending tasks, it will get away from the CPU, it will tell the CPU when it wants to wake up, and it will put itself to sleep in hardware. Yes, you could think of it as a controller. In fact, it does. Correct. The question is that a control loop, and does it use interrupts to do this magic? And the answer is yes, indeed. Correct. Yeah. Okay, great. So not many people have done bare metal programming and not had to mess directly with interrupts, but that's what we're going to be seeing here today because of async await. Makes the problem different and much more scalable. So in main, the first thing we're going to do is just for time reasons, I'll accelerate this and say that, hey, in main, there's no OS. We didn't get called. There was no loader that brought us in. So we can't leave. We can't return. We can't exit from main. Because if we did, what would we exit to? More technically, there is no stack frame for us to return to. We are at the root of the stack frame. So exiting is a problem. You're going to cause an exception, a hardware exception. So you can never leave, and that's what the exclamation mark means. You don't see that very often, but it says that this function will never return. And this way, if you forget and have a code path that runs off the end of the function, the compiler will tell you that, and you'll know about it as a compile time error rather than a runtime error. Main calls inner main because I want to be able to handle errors. Some of the operations that we do are in fact fallible, so I want to be able to reflect that. And the first thing we do is we ask the chip to give us a software definition of all of its peripherals. Remember all of those machines that are built into the chip. And those are called peripherals. And out of all of those peripherals, we're going to talk to pin 2. Pin 2 is not just a thing. It's not just a method. It's actually a type. Pin 2 is a different type than pin 3. And because I'm going to inject what pin I want you to toggle, because it's going to be the LED, I'm going to inject that into another function. I don't want the function to be hard-coded to pin 2. I want it to be any pin. So we call degrade on pin 2, which gets rid of the type. It's still a pin, but you don't know if it's pin 2 or pin 3 by its type. You now have to check its value. In other words, you have to check it at runtime rather than at compile time. But that's great, because now we can pass it into a function. And if we reconfigure the board, we can just change a number, and everything works. So we go through all of this. We then say, OK, we construct a concept, a software LED. And the reason we're doing this is I want to abstract the hardware. I don't want the users of this. I don't want people to have to worry about the low-level details, especially when the compiler can abstract that for us and make the code just as efficient as if we had worried about all those little details. Makes it much less error-prone, much more readable. So what we're passing in is the pin we just defined as pin 2. We're passing in something called a spawner, which is something from the executor that lets you create a new task. That's the only way to create a new task. So we get the spawner that's passed into us from at main. We then pass that into our LED constructor. And then we also pass something else that's called a signal. And the signal is basically a hotline to somewhere else. So when the LED needs to do something or communicate something to someone else, and we'll see who the someone else is in a minute, it can do that via this signal. Think of it like a channel. Okay? So the LED is now set up, and it's here in this binding or this variable called LED. We now have we do the same thing for the button. What pin do we want to put the button on that we're pressing? We have it on pin 13, and then we degrade, so it's not hard-coded to pin 13 in the button function. And then we create this concept of a button. So now we have an LED in software and a button in software. And what's cool is that now that we can loop forever, and we can just say something very straightforward. Wait for a button press. Now, what's happening when we wait for a button press? Well, we wait for high on the pin. Well, what is high? Certainly not the position, because the button is high when you're not pressing it. You push it down to press it. What we're waiting for is the high voltage. We've configured this button in its constructor to be an input. And so you can see that in this constructor, when we passed in the button pin, we said hey, we're going to store the pin inside the button struct, and this pin is going to be configured as an input. That means this button should have an API on it to say, is the voltage high or is the voltage low? We're not setting the voltage, we're reading the voltage. And that's what we're doing here. We're saying, hey, executor, put me to sleep, give me an interrupt when this voltage rises. And before that, I don't care. I'm going to sleep. There's nothing that needs to happen. And the executor says, I have no other tasks to run. So the executor figures out that it can go to sleep, it sleeps the CPU, and we have low power usage. Okay, once the button press starts, we will wait a certain amount of time, because as the button is being pressed, it gets to this little indeterminate zone for several microseconds where the voltage will tell you, yeah, no, yeah, yeah, no, yeah, no. And so you get a lot of, if you read it like on an oscilloscope at really high resolution, you'll see there's thousands of presses for every little press. So we just want to say, look, we got a voltage, so we know a press must be starting. I'm just going to wait for about 10 milliseconds, let all the noise go by. And now the button is fully depressed. And what are we going to do after waiting and we're fully depressed? We are going to wait for the release of the button. And when we release the button, we know how long the duration of the press is now. We can do that calculation. And if that's a short press, we'll go to the next flashing mode. If that's a long press, we'll go right back to, reset, like to the fast flash mode. And that's how we're doing that magic. Going back to main. Oh, sure, go ahead. Correct. Oh, that's a really good question. The question was, is it actually blocking? Let's say we had two buttons and we did a wait for falling edge on one button. When we await that and put the whole thing to sleep, are we now unable to read the second button? The answer is it depends on how you design your software. It would be a bug, obviously, to do that. What you would want to do is you'd want to put each of those buttons on their own task. We don't actually have a process because that's also an OS concept. There's just one execution point wherever the program counter is pointing. But what you can set up, there are hundreds of thousands of tasks. They are incredibly low overhead. So it's no problem. It's much lighter than a thread. Threads were invented because doing many processes was too heavy. Well, tasks kind of came about because threads were still too heavy. So you can do many, many thousands of tasks. So if you put both buttons on their own tasks, what the executor does is it determines if all of its tasks are waiting for something. Your software doesn't have to worry about it, right? Whatever the combination is, you don't care. Each task just says, I'm going to wait for this button press. And that gives you this principle of locality in your programming, which makes it far easier to maintain and update your program, because you don't need to worry about side effects and ramifications with other parts of your code. The executor worries about that at a much higher level and does it extremely efficiently. But that's a great question. I'm sorry? The question was, are we creating a task in this code anywhere, or is that implicit? And the answer is yes, we are creating a task in this code. I didn't show that just for brevity, but if you go into the constructor of the LED, you can see that I'm spawning something called an LED driver, which is the code that is actually turning the light on and off, waiting for a certain number of milliseconds, and so on. The button, I'm actually driving just with the main loop, and then I'm awaiting on that. So you're basically, your main is one task. You get a task for free, So I'm using that task to drive the button, and the main task is spawning a second task that I'm using to drive the LED. It's a great question. Carl? Yes. Yeah. That's right. So Carl just pointed out that, with Embassy and with async await, if you have two buttons, you can actually combine the two tasks and wait on either one being pressed. So depending on your usage, you can say await both of these. And in fact, we actually do that in this code because, again, remember I talked about a 10-second duration for a light? We do not have to wait for that transition for the light. We are waiting on either a button press or the driver saying, that's enough, I want to change the status of that LED right now. So there's no latency between when you press that button and when the hardware responds. Well, there's very little latency, right, between those two. It's not zero. Okay, great. So I'll show you guys that really quickly, and then we'll take a very short break because I want to also get to the debugger, and we have a little bit of a challenge to work through with the Visual Studio Code as well. So I want to give us time for that. So the last thing I'll show you about this code here is that code that we just talked about, where we wait multiple different tasks. Okay. So inside the LED driver, this program we just, the code we just asked about, what we do is that we're looping forever. And depending on what mode we're in, fast flash, slow flash, on or off, we're going to execute one of these match arms. So you can see that if we're in fast flash mode, we toggle the pin. So if it's on, it's off. And if it's off, it's going to be on. And then we're going to do this thing called select, which means pick one of these. And one of these is one of two tasks. There's select 3 and select 4. You can have really, any number of tasks. And so what we're doing is we are saying, I want to wait 250 milliseconds, or I want to wait for a message to come in that channel, that signal, that tells me I need to change modes. That message is driven by a button press on the main task. So we're waiting for two separate tasks. And whichever happens first, that's what we respond to. Select will return the thing that happened, and what we get is an either monad. I hate saying that word. We get this it's like a result, except you're not associating error, okay or error. You're just getting, it's either A or it's B. And so that's what happened. Either the timer went first or the message came in first. And so you're going to get this either. And so we figure out what we got and we make the mode change if necessary. And that's what the LED driver loop is doing. And each of those match arms just has a slightly different behavior. Questions about any of that? All right. Oh, question? Is there a standard graphical way of there's certainly not a standard graphical way of conveying it, but I have to believe there's a graphical way of conveying it. Yeah. I mean, if I had a whiteboard here, I could, draw one. And I think it would make more sense than just, reading text. But yeah. Once we get our single step debugger running, that should help us. So let's see if we can get that working. Okay. Yes. Yeah, so how complicated does this get if we have other LEDs or other things that we want to do at the same time? It's really important to design your software so that it doesn't scale super linearly with complexity, right? If you can get linear, you're great. If you can get sublinear, even better, right? So probably the simplest thing to do is one device, one task per device, and then you manage all these tasks. But it could be that the interrelationships of those tasks can become complex. So it really depends on what you're doing, how complex it's going to get. But I can tell you that you can write simpler code than what you're seeing here that will not scale with complexity, right? You can write code that abstracts away the details, which gives you some upfront complexity or upfront cost, but then you scale sublinearly with as you add more things. So it depends on how you want to do it. Okay, I'm going to go for a break, and let's go for a 5-minute break, and we'll come back for the debug session. Yes, sir. Yeah.
I finally got past the
Oh, for debug.
permissions according to your
Yes.
website. Now I'm getting your target device does not respond to request.
Hmm. An error occurred in the communication access.
And I verified the messages
Yeah.
as once before.
It seems to have just got that. Oh, yeah.
I've not seen that. I don't know off the top of my head why that's happening.
I just got it.
Anybody running Linux here? Gotten it to work? Yeah. Can you help with this message, perhaps? Because I'm not familiar enough with Linux. Yeah, no problem. No problem. All right. Also, anybody Visual Studio Code guru? I would like your help, please. Visual Studio Code, anyone? Yeah? Yeah. Can I get your help on something? Okay. So,
I don't have a cable.
okay. So this debugger, Visual Studio Code has a plugin which speaks the protocol that talks to this debugger. So when I hit run, actually let me shut down the other guy.
I haven't gotten this far yet.
So if I quit, I'm going to quit that guy. So I'm going to walk you guys through how to configure Visual Studio Code. And I did this like a week and a half ago, and it worked. And I was stupid. I forgot to write down some key pieces, and now I can't remember what I did. I don't use code, so this is me doing it for the first time. So when I'm in debug mode, I have the choice of like different things to debug. This thing is a CM sys DAP protocol, so it should be DAP server. It says probe-rs. And now when I run this, I should get single-step debug behavior. And I don't know what the heck that is. The problem is I can switch back to the one I did last week, and that one will work, but I have no way of teaching that to the group. No? All right.
Yeah.
I'm going to. So what I'm going to try to do is I'm going to try to go to probe.rs because these are the guys, and they're telling me easy, right? Visual Studio Code. So launch.json entry for your target project. So that's fine. Yeah. Start a debug session by launching a new process. That's what I want to do. So they give me a launch.json, right? So I'll take it. So this is gonna give me a new task. That's what I want. I just nice and simple. And then I'm hoping this is the launch.json I need to replace. Let's try it. Oh, That looks good. Could not parse PID or PID invalid digit found in. Did I copy paste it wrong? It didn't tell me where. Poor index. It doesn't tell me anything about modify or remove. Okay. Speed, modify or remove. Probe. Okay. That's the one I need. So what I'll do is I will see if the one that I have working I need. Do you know how to open launch.debug? Launch.json?
Control P.
Command P maybe? Yeah.
The other one you could just try pick. I think you just press run debug. It should say that it's going. I don't know why it's doing that. Try that. But it should like basically check the situation.
Yeah. No, there is one. This is the one. This is the installation that works.
Oh.
So
You open it? Just go to.
I just need to see the launch.json.
Go to the project like.
Project root.
The project is going to be in .exe mode and such.
Oh no, I think I moved it. Shared. User share, that's right. Nope. Crap. I'm going to try it without that super secret handshake that it was asking for. And if it's able to work, bin hex elf. Elf is default. We'll go with that. Oh boy, this is why it didn't work. Okay. I need that file because I've already figured all this stuff out. Shit. Yeah, it's okay.
These are like low-level details.
Yeah.
I was hoping to learn. And
Yeah. Well, I mean, it's only got 3 more questions for us. We're like, ah. Yeah. So let's see. Program binary, we know it's going to be called debug. What does it call it? Probe. Do you remember the name of the repo?
probe dash RS.
No, that's the. I can't even remember the name of my own code. I got so much stuff going on in my head. Blinky probe. Okay. Blinky probe. Now there's an SVD file to my target core. Oh my God. I know where that is.
I went through
Hey.
the rigmarole of getting us to work with WSL, passing
Okay.
through USB devices and such. Do you want me to open a pull request or just send a few links for the resources I referenced along the way? Just in Discord or something.
Yeah, go ahead and open a PR. Go ahead and open a PR. I think that I can take a look at it and see if we want to, as long as it doesn't disturb other people's, but it lets everybody, run. I think that would be great. Thank you. Find.
One thing you install on Windows side is
Okay, thank you. 2040 SVD. Okay, thank you. Yeah, no, I appreciate that. Okay. CP. Code SVD. And then
Oh, yeah. Mine was, I was on one instead of. Yeah.
program binary. Program binary. Program binary.
No, I'm not. I've been very impressed with your presentation.
Well,
very
thank
much.
you. Thank you. Well, that's what
Yeah.
I'm hoping
I'm
for.
coming from a different angle. I've
Oh,
done
yeah.
a lot of this shit in
Yeah.
my career.
Yeah.
I'm just barely learning Rust and so
Yeah.
but it's, the tools and tools you have to do.
Mhm.
It's,
It's pretty nice that they're trying to take a fresh look at the tooling and
yes.
making it more livable for people who
We
want to.
see a lot of that in Rust media.
Yeah.
A lot of stuff we're doing.
Yeah.
We don't have to do it the way it was forever.
Exactly. Yeah, it's hard sometimes to get change going, but sometimes it's worth it too.
I'm always
Alright.
excited about good change.
I'm with you on that. I'm totally with you on that. Oh my God. I did this work about a week and a half ago, and it looks like I forgot to write it down. And I don't use Visual Studio Code, so I am trying to figure out. I don't use Visual Studio Code, so I'm trying to figure out what I did in order to get the actual debugger running. All right, so we're gonna do this.
Just a quick update for you.
This,
Looks like
this.
my problem was that this wire here was either not connected firmly there or not connected firmly here.
Okay.
Pushing it in more, suddenly things started working.
Wonderful. Okay. Well, that's
So
great
if it
to know.
happens to anybody else, you can tell them now.
You got. Thank you. Appreciate it. 2040 Pro. Okay, so it's picking this up. Okay. Okay, let's resume. How you doing? Magic 8-ball. What's it tell me? It says free and open. All right. Love
Did
it.
you see where it came from?
No, I didn't. That's great. That's great. Very nice. Okay, so for this next part, what I'd like to do is run the same program with a single step debugger. I set this up about a week and a half ago. It went real smooth. I was like, great, we're all good. And then I now realize, not now, but about 2 hours ago, I realized that I don't know if I wrote down the steps. I do not use Visual Studio Code. Excuse me, guys. Can we get started, please? Yeah, just make sure everyone can hear. Thanks. So one of the challenges here is going to be, I'm going to need your guys' help to actually debug the debugger or debug Visual Studio Code to get this thing working. I'm a few questions away, but maybe with our collective brain power, we can get it working. So in order to debug, you need an editor that works with CMSys-DAP. It's an ARM protocol that's used fairly broadly. And so that's the language, if you will, or the protocol that we're using to talk to this probe to seize control of that microcontroller. And the editor I was just using, Rust Rover, does not speak DAP, CMSys-DAP. So for this part of the presentation, I have to switch to Visual Studio Code. Actually, let me switch over to the, I have a tab open for the editors that there they go. So these are the tools that support the Debugger Probe protocol. So if you use Visual Studio Code, Visual Studio, Visual Studio, Eclipse, nobody uses Eclipse probably, right? Emacs, you know, a bunch, there's Vim, NeoVim. So there's a number of editors here, but there's also the command line as well for GDB. And if anybody who's done that, it's probably not your favorite choice. So I would say that the list of editors so far is rather limited. This is one of the challenges with going with a newer technology is it's not broadly adopted yet. But I think the future looks brighter than the past, so it's going to be a matter of time. So for tonight, what we're doing is we're switching over to Visual Studio Code. It's the exact same folder that we were in. Created a .vs Code folder, and VS Code, for those who are familiar with VS Code, uses configuration files called launch.json. So I was on the probe.rs website, and I was just following the instructions here about, well, I'll back up a step, and it says, to the promise, easy debugging in VS Code, right? It's got to be easy. So we're going ahead into this debug section. When I look at usage and configuration, we see here that we have basically two ways to debug. We can attach to a new session, in other words, like reset everything, start over, or we can attach to an existing session. And I think to keep things simple tonight, we just want to not attach to a new, but launch a new session each time we do the debug. So start a debug session with minimum configuration. I think I'm going to try this just to see if it works. So this will become our launch.json file. I'm going to go over here. I'm going to go over here. Our chip is an RP2040. And the program binary's name in, I'm trying to remember, Blinky Probe. And if I'm lucky, do I have to what? Oh, that's a good point. The comment was, do I need the path to this? Yeah, I don't know. Well, let me see what the path is. Okay. So modify. Oh, yes, I see what you're saying. Yep, that's not a comment. Relative to what, though? That's is the create root, or maybe just. I'm sorry? Yes? Think of final slash here. Do you think we need the executable name here as well? Wow, I never would have guessed that. Let's see. I hope you're right. Like that? Is it? Ooh, well, that's interesting. Thank you. Good catch. Great catch. Still nothing. Nope, it doesn't do anything. I'm sorry, there's a lot of air conditioning here. Did I save the config file? That might be the win. Maybe, because I'm used to autosave in my. Okay, so if I, oh, I see, yep. Yep, it is saved, and I run, I debug. Let me see here. Rust Rover is not even running, so I know it is not interfering. Yes, I did in another user. I set it up, got it single-step debugging. I was like, I tried that. Unfortunately, I don't have that. This needs to be. Oh, it's a key, right? Okay, so where this is a key value pair. I was reading the right side as a comment, and thank you. Duh, of course. Come on. That's not it. Maybe this is not the right path. Let me do this from root. Okay, that's the full path. Really? Default build, probe.rs debug, launch, flashing enabled, core config. Let me just see if this is valid. Okay, so that's the right path. What if I add, oh, click this button? Oh, it just gives me more things to choose from in this drop down. It's going to make, this is one configuration. So it's just going to let me add more configurations, more of these settings. And that's one way. If I was running multiple different boards, I could presumably debug different boards with different configurations, because it's an array of configurations. Say again? I hope not, but that's a good one. Is chip case sensitive? RP. There could be a dash in there. It's like this. Yeah. And yours is able to debug? What's the does your launch.json, is it the same one? Did you copy it from the probe.rs website like I just did? Yeah. Yeah, that's what I had. Yeah. And it debugs on yours, eh? All right. Well, why don't bring one of your computers up and we'll debug. We'll show that it, we'll show it running on one of your machines. I'm not sure why it's not working on mine. Yes. Because otherwise, we got a room full of people waiting for something to happen, and we don't want that. No, that's right. That's right. Yeah. Yeah, there's a few questions in that template that I do not know how to answer. Okay, so could I get you to join? Yeah, I know. You got to join. Go to this website to join the conference. And I will. It doesn't matter, yeah. Stop sharing. All right, so I don't. Okay, so I'm not sharing my screen anymore. Okay.
So we can share the screen. Let's use the whole.
Cool. Great. Awesome. Thank you, sir. Yeah. Thank you so much. Okay. So, all right. So what we've got here should be the same. It's what? This could be why. It's right. Nothing gets by me. Oh, boy. Wow. That's okay. I wasn't expecting to need a magic adapter. I was just gonna, yeah. How do you like your framework? I used to, when Macs went all Johnny Ive and they only had USB-C, I lived in that world. I don't miss it though. But you've got configurable ports, so
Yeah.
How do you like your framework?
I think it's really fun.
Yeah.
I enjoy it.
Oh, cool. Now it has HDMI.
Yes.
Thank you. That's right. All right. Do we have signal? Okay. Okay. Thank you guys for your patience. Okay, so here we go. We're in the same repo. What we're doing here is we have this launch.json file, and you can see that it's configured with the program binary pointing at the debug Blinky that we've just set up. And now when I click run, I don't want to start. I just want to cancel. I have to hit the X square. Okay. All right. Flashing device, it says. It brought up a little. Okay. So what we should see here is, I don't know. Yes, it is. Yes, it is off the bottom of the screen. I don't know how to resize the screen on this machine. This is not a Mac. So yeah, that's about 2/3 of the way down your actual screen. That's not the title bar. Shit, I can't. Okay. All righty. So I'll stop this guy again. We'll do this one more time. Run. Cargo build. It's flashing the program. And now we have, do you see the debug controls over here? These should be pretty familiar with anybody used to debugging. So I guess we should have set a breakpoint. But yeah, we can pause it. And what it should be showing us now, if I could shrink this window. Okay. It's showing us where it's paused. So I can do step over. Okay. Now why it's showing me assembly language, it should be showing me Rust source code. Let me, yeah. Let's set a breakpoint on main. On main. And let's say we want to stop right there. So then debug, build. So now with a breakpoint set, hoping we stop. And then if it's not step over, nope. No, it does not seem to be working. What it should be doing is stopping and highlighting the line where the breakpoint is set, showing the current status of all the variables. probe.rs will actually read the variables into Rust types. So if you've ever done any debugging and you sort of are using C types and you notice the debuggers are not using the Rust data types, you would be pleasantly surprised here. Are your machines single stepping at all? Can you set a breakpoint and it single steps? It does, right? Okay. Well, that's too bad. Let me see here. I want to try one more because I would like to show the group this. Could I? And you have a Mac, so I'd be more comfortable demoing on that one. We're going to try one more time. Stop sharing. Cool. Demo gremlins, eh? All right. Thank you, Chris.
No problem.
We tried.
Too
We
bad it
tried.
didn't work all.
That's right. Close, close. All right. So here we go. And can I have you go to this website? All right, so we can continue using the browser.
Try to start the adverts. Yeah. I haven't run Teams in quite a while, so it's.
Oh, we can just use the, we don't even need to. There.
I didn't connect to the Wi-Fi, so it's my tablet. Let me bring my tablet closer.
Okay. If it doesn't want to,
Microsoft Teams doesn't have that. You know, it's like they go into little, there's like a little station bar.
Yeah.
Basically, virtually.
yeah, I already killed it. It's dead. Yeah, we're good. Use your microphone. Thank you. Allow. We can turn off the camera. Where's the camera? Background? Oh, that's camera. Okay. And what's your name?
Scott.
Scott? Okay, thanks. Okay. And then go here. And then share. It's okay.
Looks like we have to join the tab. This Edge didn't have this screen sharing permission.
Okay. I think we have to quit edging out, re-enter it though. Yeah. Looks good. This site will be able to see the contents of your screen. Yeah. Oh, maybe you click entires. Maybe you click that and then share.
Oh, I see. I think that's okay.
Wonderful. Thank you very much.
Yeah, sure.
All right.
I'm gonna put this by.
Okay. Okay. So all right. So what we are doing now is we're going to try the same thing, third time's the charm. So we will stop the one that's running. We will debug, cargo build, flashing the device. Okay, so it is running. If I pause, I'm seeing this inner pole, same thing as we saw on the Windows machine. What I want to do is set a breakpoint. So we'll go to main. And we'll try to do this again where we set a breakpoint right here. We'll try to debug. What? only took 3 computers to get it. Okay, so this is what we want to see. Here we go. Thank you, Scott. Appreciate it. So you can see here on the, oops, that I just collapsed it. On the right, we have a call stack. So the debugger is telling us how far in we are in our program in terms of function calls. As I step through, a single step here, you can see we've got all kinds of information about where we're going to break, what peripherals. No, we want variables. You say view at like here? Yeah, I'm used to seeing it show up. Like when I did it on my machine, it was over here on the right. But all the variables as they get defined just start showing up, and then you can query their values. You can change their values while the program is paused, and that way you can inspect and do this type of debugging. But I'm not seeing the variable names show up.
Might be another of those blank figure.
Yeah, it might be. Sorry? I can't hear it. Yes. Thank you. Thank you, Ava. Yay. All right. You'd think that would be open by default. So now here we can see what we're doing, right? We can see that we have a spawner, which is a thing that came from Embassy Executor. We don't know what that is. The perifs variable, which we set here in line 34. We have LED pin. We can see now that it's any pin is the type, and the value is 2. That is different than the type being pin 2 with no value whatsoever. So that's what degrade did. Let's go one step further. We'll step over the constructor for LED. Ooh, we did spawn a task in that constructor, so that'll be interesting to see if that is why it behaved that way. Oh, that's interesting. So we might have an issue where this probe is not compatible with asynchronous code. That may be why we're seeing this assembly language. Okay, so one way that might work to get around that, if I go back up here, back to main, So I'm going to set the breakpoint, not here where I'd step over. I'm going to set the breakpoint one after, and I'm going to see how we do. Debug, probe, build. All right, so we now stopped here. So as long as we're not single stepping, controlling the CPU while it's launching an asynchronous task, it seems that the debugger is happy. So that does seem like a probe-rs limitation or bug. But you can see here that the LED constructor has run. Here is the LED. And now this is a Rust struct where you're seeing the, and apologies for the small text, but you're seeing the mode field, which tells you whether it's in fast flash, slow flash, or whatever mode. So the debugger is actually inspecting native Rust data types. Okay, sender is part of the Embassy it's part of the Embassy Executor Library, or Embassy Sync library, I'm sorry. And so what's nice is that you can see, even though this is not our type, it's coming from a dependency, we are fully inspecting this thing at runtime. And if we wanted to do bad things, we could do bad things. Not R, but maybe a 0, right? You can change the value of pointers. You can change the value of variables at real time to cause the execution to go in a way that you want to inspect. So what we were supposed to do today is I was going to switch you over to a second branch in this repo called bugs. So if you git check out bugs or git switch bugs, what you'll do is you will get to a point where the code was code complete, but a couple of things were missing. And with code of this complexity, not crazy complex, you run it, nothing happens. Now you've got a problem. What do I do? How do I figure out what's wrong? You're stuck. That's why we wanted to have code that had at least a little bit of complexity. Had we not had these issues, we could debug that situation together using this debugger. That was the plan for tonight. So maybe that's homework. Maybe we'll try it again another time. We'll see based on people's feedback. But anyway, that's all I had for tonight. Any questions before we wrap? Okay. Well, I'm going to be at the, I'll be at the Flat Stick Pub tonight, so we can chat more afterwards about random things. That's fine. All right. Thank you, everyone. Appreciate it.